Hey everyone! Have you ever wished PyTorch could just handle tabular data without needing to worry about whether or not you have some feature that can explode the activation or the gradient, or a feature that contains none, or a feature that doesn't normalize well? Have you ever wished that you could just give all the feature to some sort of PyTorch normalization layers and get all the features cleaned up with a sensible gradient? If you did, I think this package might be the right thing for you. It's called PyTorch Normalizers, and today I'm going to present a specific class that's called Smooth Buckets, which is a differentiable generalization of feature bucketing. So, today we're going to talk about how we can use it, we're going to see what results we get by using it, and then we're going to show the magic of how it actually works. So, for how do we use it? Just pip install PyTorch Normalizers, then from PyTorch Normalizers import Smooth Buckets, and that's it. To showcase what it does, we will import a dataset from a Kaggle competition. It will be a house prices dataset, and its numerical features look like that. But because we're going to present a default catch-all features kinda layer, we're going to ignore what they actually are. We just want to see what it does out of the box. As for the PyTorch model, it's going to be very simple. Just input goes into that normalization layer, then it goes to output, which is of size 1, then a sigmoid activation. And the alternative model that we'll compare to will be none to none to get rid of the nuns. Then we do a batch norm, which is the alternative normalization, then a linear dropout, and the same finish to the model. Well, doing that, we get 5 different results. One is the default PyTorch batch norm results, which is 0.89. Result number 2 is the same model, but we're going to corrupt it. And we're going to corrupt it by giving an outlier near the end of training. And that outlier is hitting the model after it has already learned what the batch norms look like. It has already learned that the variance for some of the feature is very low, and then it gets something that's 100 times bigger. So that's an extreme outlier. It explodes the gradient, explodes the model, and the accuracy drops by a lot. Compared to that, we have the smooth buckets accuracy, which is higher. We have the corrupted smooth buckets accuracy, which is lower than the not corrupted accuracy, but losing one batch near the end doesn't explode anything. So in that sense, it keeps the good attributes of default deterministic buckets. And to compare that, we have the cat boost benchmark, which I think showcase the power of that layer. Now, where is the actual magic? And the actual magic is here. So when you initialize this layer, all you have to give it is a numerical feature sample. It can be a NumPy object, it can be a tensor, it can be your entire data frame for the dataset, it can be just 10,000 sample rows from your data frame. It will work. It just needs a sample of the numerical feature to get an initial guess for the means and the standard deviations of each feature. Now, what it actually does is divided into 3 steps. Step 1, get rid of the nuns. And when we get rid of the nuns, we don't want to just use mean imputation, because when nuns come, they're not always uniformly distributed across whatever distribution the feature has. Sometimes they're concentrated within a part of the distribution, and just taking mean is not very good. For the same reason, taking 0 is not very good, so we want to take something that is trainable, and we want to initialize it sensibly. So what we do is we initialize a trainable parameter at the mean of the distribution. But that also wouldn't work very well, will it? Because if we actually initialize something at the mean of the distribution, let's say 2002, And then we see, we learn, we find a good value, we try to optimize it, but we use Adam, or maybe we have some sort of L2 normalization over the weights. So if we do, it doesn't matter what is the right value that makes our loss lower. The regularization is going to push it very strongly towards 0, especially if it's an L2 regularization and it's in the order of 2000 and all the other features are in the order of like 3. So actually having a trainable parameter here will not work. It will be the same as mean imputation or 0 imputation in this case. So what we do is fix the mean and then multiply it by a trainable parameter, which has a reasonable range. It starts at 0. It has a hard-coded +1 here. So we just have a trainable mean without getting hit by the optimizer. Step 1, got rid of all the nonce in a sensible way. Step 2, we are going to create standard distributions. For each feature, we're going to create num-bucket standard distributions in the following manner. Let's say we have 4 buckets. Then our initial guesses for the means would be percentile 20th, 40th, 60th, 80th of the distribution for that feature. And our initial guess for the standard deviations will just be the distance between one peak and the next peak. Now, we get bucket share. And what is bucket share? Bucket share is essentially only the density for the distribution, and then softmax is applied. And the reason that we call it bucket share is that, let's imagine for a second that the standard deviation is very, very small. Let's say it's epsilon. So when we look at the density over those 4 distributions, assuming that the standard deviation is very small, the softmax will just give 1 to the closest distribution and 0 to everything else. It will become a vector of 1, 0, 0, 0, or 0, 1, 0, 0, and it will be just the old bucketing. We just have 4 buckets and the input falls into one of them. However, in how we initialize these distributions, they have quite a large overlap. So we don't fall into the pit trap, and we have differentiable weights for the means and the standard deviations, and we avoid the fundamental problem with feature bucketing, which is discarding data before we even start training, like losing the resolution of the data. That is the thing that we avoided in this step. Now, in the next step, we get another variable that we compute here, and we call it approximated percentile. Now, what it is bucket share times a range. So imagine that we have 99 buckets, and a range would be 1, 2, 3, 4, 5, 6, 7, up to 99, and the standard deviation is still very low. So if the input is very close to the 7th bucket, then the 7th bucket gets 1, and it's multiplied by 7. So this part actually gets the percentile. Because everything else is 0, it's just 1 multiplied by 7. We get the actual percentile, because if someone falls into the 7th bucket from the start, it's in the 7th percentile. Of course, that when actually training, this is not epsilon, and this is a bit fuzzier, and it shifts a bit because things are trainable, but it is a very good approximation of the actual percentile. And when we get a good approximation of the actual percentile, it has a very unique attribute that we would like to use. And that unique attribute comes in the following layer. So let's assume that we have 2 features. One, let's call it house size, and the other, let's call it air conditioning strength in watts. So if you take those 2 features detecting an anomaly such as house size in the 90th percentile but air conditioning strength in the 10th percentile is suspicious. It might indicate something bad about this specific house, and maybe the price should be lowered to account for that. Now, it's not mandatory to have percentile in order to learn that. You can have a couple of dense layer and just learn that from the actual raw numbers or from anything else that uses those raw numbers. But when you have these percentiles, a single linear layer suffices, because let's subtract the AC strength percentile from the house size percentile. Well, if it's very low, we're now very suspicious. So it helps. It helps and it makes sense, and it reduces the number of parameters that will be needed later. Once we have those bucket shares and percentiles, we apply layer norm, because if you remember, bucket shares sum up to 1 for each feature because of softmax, and we want to sum up to something that's more easily trainable. And that's it. We just project it to the original num features and have the results. So what we have is a layer that can normalize all numerical features. We don't have to worry about any features acting badly, and we can just take, let's say, 1,000 columns without any fear that, oh, the 97th column is going to have an extreme outlier and all the gradients will explode. So we need to remove risky features. We don't need to do that anymore. And we just get an out-of-the-box, layer for layer, same size, that actually makes sense and is safe. Thank you all for staying for this talk, and see you next time.